All right, so welcome everybody. My name's Onita Basu. I'm a professor in environmental engineering at Carleton University. I'm also an associate vice provost in grad studies as well there. So, just keeping things busy. Today, I'm like super happy to talk about what I'm calling filtration in focus. So what I wanted to do today was I'm going to talk about filtration in drinking water. And I'm going to talk about a bunch of different kinds of filtration at the beginning, and then I narrowed it down to like kind of two-ish parts of filtration in particular that I wanted to share with everyone. My goal is to kind of give you like a balance between like maybe just like practical things about filtration, since we're all hopefully or either directly or side associated with like water sanitation and hygiene in different aspects from this perspective. So before I get started, I will just advance my slide and just say a little bit about my research group. So I kind of have like four pillars in my research group: water treatment, wastewater treatment, carbon transformation research, and collaboration and education. And although they're individual pillars, they all have kind of like, like an overlapping Venn diagram of relationships, especially, the one on the far right of your screen, which says collaboration and education. So for the way that I position my research, it's like very collaborative, working with other people for the most part. So that's like the center, I would say, of like my diagram in completeness. And then the other sides are associated with it. And of all of the stuff that's there, you can ask me about any of these later on, but I'm going to focus in. Uh, Today, I'm going to focus in mostly just on this one right here. But before I get there, I did want to just share a couple of facts. Some of you may know these facts already, some of you may not, so that's why I'm sharing it. So and this is Canada centric. So Canada has about a little around 3,000 water treatment plants. And these are ones that are like servicing like populations of, about 50 and larger. But what people don't often know is that about 60% of our water treatment plants are actually for small drinking water treatment plants. And that's populations that are less than 500 people. And I also want to add on that is like the definition of the service size of a community kind of changes depending on the reference that you're looking at. So I've gone with a federal document that's positions it at less than 500. Some people use less than 300 for these numbers, so they're a little bit flexible. And then interesting on that side for the third point there, but small drinking water plants, although they're 60% of the plants that we have in Canada, they only service 15% of the Canadian the Canadian population. So I find that sometimes our design of small drinking water treatment plants is not as appreciated as it should because we only see it as a small number of people, but it's a huge number of actual plants, right? And this comes down to the idea that I want us to understand filtration better because filtration is one of the most common and key treatment aspects in a water treatment plant. So understanding any version of filtration is always going to be helpful. And then on my last little note, which I thought was interesting, that about 85% of supplied drinking water in Canada is actually from a surface water source. And that if you happen to be in a small and remote community, you are more likely to, however, be on a groundwater source. So just trying to like flex how we think about the implementation and the design of our water treatment, especially because when we're in university, we mostly consider sort of like urban large scale design versus small scale design. Okay. So now I'm going to jump straight into filtration. I'm going to say that in water treatment, hopefully people have a little bit of an idea of a water treatment plant, but in a general water treatment plant, there's different ways depending on the quality of the water, of course, but it's typically sort of like coagulation, flocculation, some kind of sedimentation to reduce the solids load. And then we go into like different kinds of filtration, right? And then that front end of coagulation, flocculation, sedimentation, it can be flexed as well depending on the quality of the water that we have. And then for filtration types, I sort of listed the most common filtration types that we have. So conventional biofiltration, those are kind of joined together, which we'll see in a moment. Slow sand filtration, green sand filtration, biosand, ceramic pot, and then membrane filtration. And then within all of these aspects of filtration, some fit better into an urban center and some fit better into a decentralized or remote community. So I've tried to break it down into like these two groups. So if you look here, the groups go like this. I realized afterwards that maybe it's not clear which way the groups go, and then this way here. And you'll notice that there's two in particular that are in both groups. So they have some flexibility in them. So we use conventional and biofiltration more in urban centers and centralized systems. And slow sand also fits there, but slow sand, you can see if you hop across here, could also be in a remote or decentralized. And I've also listed it as high tech and low tech. Super confusing. I'm hoping to cover off some of the reasons for that as we go through the talk today. And then green sand filtration. Green sand filtration is for groundwater systems where we're looking to oxidize various materials that are in the water. So it's a special subset, and then membrane filtration as well. But if I had more time, I would talk about all of these in more detail, but I've picked conventional and biofiltration, a little bit on slow, and then ceramic pot filtration, which I'm hoping to entice people to think about a project in Tanzania that you might want to join when I get to the ceramic pot filtration section as well. So I'm going to start off with just a little bit of an overview here. So first of all, again, because I think we all come from varied backgrounds. So if you haven't seen a cutaway of a filter bed, I wanted to make sure you could see what they look like. So I've labeled this one as conventional rapid filtration and biofiltration because the overall bed is the exact same, and the primary goal is particulate removal to reduce turbidity that would otherwise be in the drinking water. And it's typically in a dual media situation with like a top layer of anthracite or granular activated carbon. That's what GAC is. And then beneath that, you can see the support system. So these two layers here are our media layers that we use for particulate removal. And then the bottom here is just, this is like support for the above layers. And then there's like an under drain system to collect the water. That's a traditional system. They are still popular. They still exist. There's also more modern ones that are much more kind of like efficient. Instead of having all of these layers to support the media, you have a geosynthetic liner, and then you've got a more compact underdrain system as well. There's some other things associated with it, but these are kind of like the main parts of it. Now, when we talk about filtration, there's a couple of key controlling terms or factors that are associated with filtration. So the first one is known as the hydraulic loading rate, sometimes referred to as the surface loading rate. Always fun when you're new to a topic and you have to know that you have two different terms that mean the exact same thing. And, you know, as an engineer or a designer, you have to be familiar with what the people you're working with prefer to use and be comfortable with that kind of switch in terminology. And the hydraulic loading rate is a term that's used to kind of like normalize how we consider a filter to operate. So it's just the volumetric flow rate over the surface area, the top surface area of the filter. So it's Q over A, and then you get a meters per hour term, and that's your hydraulic loading rate. And we use that because you can imagine that there's all sorts of different filter configurations and flow rates. So if someone tells you they've got some volumetric in an area, it's harder to know if it's similar to another filter or not. But if you just use the term, the HLR value, then you're like, oh, okay. Once you're familiar with it, you're like, oh, okay. So I know this is similar to that other filter that's at that other plant over there. So maybe I can use them to compare against each other in some way. And then another important term is the empty bed contact time. So the empty bed contact time is how long it takes water to flow through the two media layers right here. And we use that as an indicator of how much time the particulates or potentially the organics in the system have to contact the filter. And it's another kind of design feature. There's some values that people usually play with. It's about 3 minutes to 20 minutes is a pretty common empty bed contact time. Then there's the media parameters. So D10 is the smallest media uniformity coefficient for UC, and then D90 is the largest one. And then the last one is backwash, and I'm going to talk a lot about backwash in the rest of the presentation today because I don't have time to talk about everything, but I will talk about the backwash. All right. So before I talk about the backwash, I did just want to hit on the difference between a conventional rapid filter and a biofilter. So the conventional filtration focuses on particulate removal only, so just turbidity. We want to get rid of the turbidity that's in the water so that we ensure that we've got nice clean water coming through into the disinfection system, and then it's safe to drink. Biofiltration looks at allowing for the growth of beneficial microbes within the filter system so that we get particulate removal and we get the removal of disinfection byproduct precursors. That's the DPB that's listed on the diagram, by reducing the DOC, the dissolved organic carbon that's present. And then it also limits bioregrowth within the distribution system. So there's lots of benefits to biofilters versus just conventional filtration. Someone should 100% ask me, why doesn't everyone just use biofiltration at the end of this talk? Okay, so when we have a filter, so again, I've just got a cutaway here on the side, right? So we've got our filter, the water's going on, we've got 2 layers, some support, and then out it goes. Like, what does that actually look like? So we can think of, if you have a Brita filter or some other filter at home, we just pour the water in and out it comes. And usually we just drink it like right away. But there's a really important part in a full-scale filter system that you have to know about. If you may know it about already, and that'd be great. And that's this, when you first put a filter in service, there's this weird little spike of turbidity that happens that we call the ripening phase. And then we can actually use it for production of water for drinking. And then eventually at some point that filter is going to get too dirty and we have what's called breakthrough. And that's when we need to clean the filter. So this part on the right is known as conditioning. And it's due to remnant water. So dirty water that was already in the system from the last backwash. But also filters work better when they actually have a little bit of particulates on them. So as soon as we have a little bit of particulates on them, those particulates that start sticking to the media, they start allowing us to pull more particulates out. And so that's what this little bump kind of represents. And then we get to breakthrough. And that's a theoretical one. So I wanted to show you like a real one from like a real plant. This happens to be from the city of Ottawa, where we've got turbidity on the left-hand axis and we've got time on the bottom, and we can see the spikes. I've just shown 2 curves so that you can see, and actually you're going to see a bunch of these as I go through the talk anyways, but just so you can see some real data. Okay, so now I'm going to focus in on backwashing. So we know from that graph that like we're going to remove the particulates, but at some point we have to clean that filter bed. So how do we clean the filter bed? So there's kind of 4 ways that we use to clean the filter bed. One is with water. So we reverse the flow through the bed, and that helps to remove the particulates. So I have a video here. Yeah. If you look here real carefully, you can see the water going up. That's a bass. He might be in the talk listening in. That's one of my grad students. And that huge plug of dirty water is us having reversed the flow. And if you look closely, you see it starts to get clean. So we're getting rid of all the dirt that was there on the bed. Okay, so it's kind of cool to see that in action. So you can do that with water. We also have an air scour, which is when you add air to agitate the bed itself. And then that allows for more particulate matter to be removed. There's another step called extended terminal subfluidization wash, very like long and fancy sounding, which is why people always just call it ETSW for short. It's a lower water wash rate, so it's a very gentle water wash to help remove like small particulates from the bed. And then the last one, which I don't have time to talk about, and I probably don't even have time to talk about everything anyways, is a surface sweep agitation. And that's like when you have like these rakes of like a bar of water, a pipe that circulates around the top of the filter to just kind of help break it up. And I've kind of listed some of the important factors below that. And what I wanted to show you, if you haven't had a chance to be at a water treatment plant, so the first video that I just showed was like the side profile cutout. You can see like the water moving up, and that's cool. But if you're at a full scale plant, like what does it look like? You see these like filter beds here, right? And that's just kind of what you see. And then they get filled with water. And then the first one, in the stepwise process, you actually do air scour first. So all you would see is this. You'd see the kind of like the bubbling of the water happening. It's agitating the bed. You start to see the remnants start to get dirty and move up. When you do the air scour, you're not trying to push the water out of the bed yet. You're just trying to agitate the bed to make the particulates loose. Then you go into your water wash step, and that's when you like keep increasing that water, and the water flow goes up, and we sort of saw it was going up and then it went into an overflow. And so here you can just sort of see it all overflowing out of the bed here, very dirty. And then the very last step, if you have it at your plant, not everyone uses this, is this ETSW step. If you compare the middle one to the left one, hopefully you can see that the far right one is a little bit less dirty than the one in the middle. And it's too hard to see, I think, on the screen, but you can see little particulates that are sort of like coming out of the bed still. If you look closely enough, you can kind of see them there, maybe. Anyways, I just wanted to give you guys an idea of what those looked like. All right. Okay, so that was so you could see kind of what it looked like. And then if we continue to kind of analyze what's happening, so this is some research that we've done. So air scour versus hydraulic backwash, does it matter? In some plants, you only have a hydraulic backwash, and in some plants, you have air scour with the hydraulic backwash. So here we've been doing a study at a plant that only had hydraulic backwash with some really old media in it. And we also compared it to an air scour. So what I wanted to show you was, if you look at this diagram, let me just explain it to you. On the left-hand axis, I've got turbidity. So this is like the turbidity of the media that's in the bed. The bottom axis here is the depth of the bed. So it goes from the top of the bed at 5 to the bottom of the bed at 75. And I forgot to write centimeters, so sorry about that. So it goes from 5 to 75 centimeters. And this little red dotted line is kind of like the goal that we want to get to in terms of how clean the media is after we backwash it. So in this particular filter bed with a hydraulic only backwash, we were having a hard time, as you can see, getting to the media cleanliness that we needed to get to. Now, at the same plant, they had another set of filters that were newer and had air scour added to it. So what we can see here is that before the backwash, I mean, we always expect before backwash to have lots of like particulates that are captured in the bed, because then it's doing its job. So we've got this large amount of particulates, but then with the air scour, all of the media was very, very clean. So it was showing that the addition of the air scour was very helpful in terms of like getting rid of like sticky particulates that were otherwise stuck on the bed. So when we did this particular research, it doesn't mean that the hydraulic backwash won't work or can't work. It means that this is an indication that you should change the way you're doing the backwash. And this is a good way to check if you need to change the way you're doing the backwash. So like, can you increase the velocity that's going through the bed? Do you need to increase the duration that you're washing the bed to kind of get the particulates a little bit better? Or maybe it's something else. And then just to throw in there for the air scour, so the air scour clearly works very well. But if you're trying to have a biofilter, then there's a question mark that comes up. Like, at what level is the bed too clean? And we may impact our DOC removal, which is the organics removal, if you also happen to be trying to run your bed as a biofilter versus a conventional filter. If you're just running it as a conventional filter, it doesn't matter. But if you're trying to get a biofilter and you're like really like cleaning everything vigorously off the bed every single time, you might run into a problem with your DOC removal. And I made a note, this is a very understudied area of research. I do have a little bit of research in this area, and it's something I'm interested in doing more on. So I've done one study here where we looked at the impact of the hydraulic backwash on DOC removal. So I'll just explain the graph to you for a second. So here I've got percentage DOC removal on the left hand or the y-axis, and here this is different versions of the hydraulic backwash. So when we backwash a bed, even though you impose like a water velocity on the bed, people often refer to it as a bed expansion number instead. The typical bed expansion is between 25 to 50%. And that's a recommendation for conventional filters. There is no recommendation for biofilters. So people just kind of use the conventional one all the time, but it's still something that needs to be looked at a little bit more. So here in this particular study, we were using 30% as a baseline for backwashing the bed and achieving around 35% removal with some pretty big error, like, you know, standard deviations, error bars as well on it, which is pretty typical in biofilters. And then what we also did was we looked at 20% and with the same volume as the baseline or same duration as the baseline. Same duration meant with a 20% expansion, it's a lower velocity, so you end up using less water. And then same volume was trying to do the 20% expansion for a longer time to use the same volume of water because we just wanted to see how expansion worked. And the main point here was that we could decrease the expansion and save on some water for cleaning and still have no impact on the DOC. But when we increased the bed expansion, which is like an increase on the force on the bed, so it gets more agitated, we did see like a noticeable drop in the DOC removal. So it went from like 35 as a median down to around 25 as a median value. So it shows us that, yes, how you backwash your biofilter would matter, and it's something that should be looked at a little bit more. Okay. Now not the last one. For this particular set of filters that I wanted to talk to, I also wanted to mention extended terminal subfluidization wash. So not all plants use ETSW as a wash step. It's probably, I'm trying to think of it, it's probably around 25-30% of facilities use ETSW as part of their procedure. So the goal of ETSW is to minimize that spike that we see at the beginning of ripening. It decreases subsequent particle release, which allows the bed to go into service faster, which allows for a larger production of water overall. So what I was showing in this particular research, you can see I've got something labeled B1 and C1. So B1 stands for biofilter, C1 stands for conventional filter. And in these cases, the filter is operated fairly similarly in terms of their turbidity ripening spike, which we can see here. And then I had a duplicate test that we ran. And so you can see it here. They had slightly slower ones, but they were run at the same time, and they had the same kind of overall pattern. So no ETSW. And then if you look at when we add the ETSW here, we lower the spike quite a bit, which allows us to potentially put the water, to use less water and to put it into service faster than if we're worried about a really large spike happening. And you can also see another test that we ran. So we used turbidity, but we also were monitoring for like particles in particular. So we did a particle count on it. And the upper line here is if there's no ETSW step, and then the lower line here was with an ETSW step. So we end up releasing less particles from the bed. So we're overall trying to increase the safety of the water by decreasing particulates that could go into the distribution system if you incorporate an ETSW step. All right. So for time, I'm now going to skip to slow sand filters. I'm hoping this the way I'm doing it creates lots of conversation for you. So slow sand filters look very similar to a biofilter or a conventional filter in many ways if you're going to like a full-scale plant. So here is a picture from a full-scale plant in Canada as well. So you just see like the top of the filter bed and then here, but what you'll notice perhaps is that the surface is sand. So when you have a slow sand filter, you don't have, it's a monomedia filter with no granular activated carbon on top. It has much lower flow rates associated to it. And the water volume or the water above the bed has to be controlled more strictly. And the reason we're controlling the water height above the bed is because in this case, it's also a type of biofilter, but it's like a more intense biofilter. All right. And so the more intense biofilter is because the biofilters rely on microbial activity to help remove dissolved organic carbon. The slow sand filter also relies on microbial activity to remove dissolved organic carbon, but it also helps remove the particulates that are coming into the bed because you allow for a larger amount of the slow sand filter to the biomass to develop over the slow sand filter. And with this biomass amount, you create a lot of EPS, which is what microbes excrete, so extrapolymer saccharides, and that maximizes the capture of particulates. And slow sand filters are also a bit better at removing bacteria directly because the healthy microbial population then predates on a bunch of the pathogens that are present in the slow sand filter as well. So they're both biological, a biofilter and a slow sand filter, but you could say the slow sand filter is more biological than like a regular biofilter happens to be. Now, I had mentioned earlier that slow sand filters are both low tech and high tech. And so here is where it becomes more of a high tech option. And so it's not uncommon, especially in Canada, where we have slow sand filters in smaller communities. It's very useful in the fact that smaller communities have larger areas. It helps ensure a higher degree of bacterial removal or pathogen removal from the system. The slow sand filter itself doesn't require a lot of operator interference on a regular basis with it. So that's the advantage of it. But if you want to kind of maximize the efficiency of the slow sand filter, people put in these ozone contactors, which are really great. So the ozone contactors take large organics, make them into smaller organics, and then it helps the bacteria predate on them. So this is where we end up going from a simpler system to a more complex system, although they can be very compact still. So that was all I wanted to like spend time on the slow sand filter, but you can ask me more questions about it as well. Because I also wanted to leave a little bit of time for talking about another type of filter system, which is a ceramic pot filter. So the goal of my talk is I've gone from like conventional biofiltration, like big urban centers, slow sand filters, which is kind of like smaller locations or big locations, and then down to point of use, which is also a filter system, which is a ceramic pot. So in the ceramic pot, which is used in a lot of low middle income countries. You can just see it just looks like a flower pot, fits into a nice little basin here. And then, home washing to like manage it and to keep it clean is how they kind of function. And how they're made, because they're not exactly a fat flower pot, they are a little bit more complicated. So in terms of the way they're made is it is a pot, but it has a sawdust and colloidal silver added to it. There's an option where you don't have to add colloidal silver. The ones that I'm working with, we always add colloidal silver because it improves the disinfection efficacy of them as well. But you add silver and you add sawdust to it. And then when you put it in the kiln, the sawdust burns away and leaves a porous ceramic matrix. The silver stays inside, and then you can use them for the local economy. And when we use the ceramic pot filters, they're from the locations that we're working in, so they're nice that they support the local economy. But I always wanted to like emphasize a little bit on how they work. So if you look at a cutaway of it, right? If you could zoom in on the lens of it, what you'd see is this porous matrix with silver embedded in it, so that when the contaminated water hits the surface of it, what happens is obviously the water starts to filter through most of but not all of the bacteria get caught above into the pot itself, right? And then we have clean water that's coming through, or cleaner water coming through, right? That clean water has small amounts of colloidal silver in it. So because some of that bacteria will transition through the filters themselves and end up in that water, the advantage of having a colloidal silver in it with the bacteria is that the silver then acts as a disinfectant and kills the microbes that are present, so that you ensure that the water stays safer to drink for the local population that's using them. Okay, now the ceramic pot itself has a lot of like technical factors associated with it. But in this case, I think when you're using a ceramic pot filter, the community involvement and engagement is critical to the success of implementation. When we think about like working with the city of Ottawa on their filter systems, like we can just work on the filter system with the plant or other communities, and we don't really need to like engage the population as much. But when you're working in a low middle income country, and especially when you're utilizing point of use devices, it's critical that you work on community engagement, because without the community engagement piece, nothing else matters anyways, right? So that's like a super important part on it. And also doing long-term studies are needed on the filter use in the fields. I have up to 2 years of data on use in the fields, but we're looking at doing some longer term research at this time to see how everything is functioning. These are just some of our pictures on that side. Okay, and then just quickly-ish, because I want to stay on time, I kind of wanted to show you the breakdown between the conventional filtration and biofiltration, slow sand, ceramic pot, and then circle back to kind of where we said they were used in the beginning, right? So conventional filtration and biofiltration takes up smaller areas, has higher flow rates. I've listed the hydraulic loading rate there for you to see, 5 to 15 versus 0.1 to 0.4 for slow sand, right? Where they kind of fit in depending on how you like build the system. And then looking at the ceramic pots, home operation, lower cost. Lower cost is the relative term because it may be low cost to us, but high cost within that particular community. So that's another like social factor that we definitely have to take into account on that side. All right. And of course, this project was not possible without many, many, many people and many grad students involved in it so far, and hopefully moving into the future, and several funders and organizations that have been involved in that research as well.